The first example that I want to show you is rotational inertia of a uniform rod, and I will do this one with integration. The question is, what's the rotational inertia or the moment of inertia of a rod about an axis that is perpendicular to the rod and passes through the center of the rod. So here is the rod. It has a total length of L. It has a total mass of M, and the axis of rotation passes through the center of mass of the rod. So I'm going to also introduce a one-dimensional coordinate axis X, like so, passing through the rod lengthwise. And since this is a problem that must be done with integration, I must select a small mass element in the rod with mass dm and length dx, and then do the following integral, which is the definition of rotational inertia. So I is equal to the integral of r squared dm. So here is my rod again, and the left end of the rod will be the lower limit of my integral. The right end of the rod will be the upper limit of my integral, and I want to integrate over the length of the rod. So I'm going to have to switch variables in order to do the integration. So I'm going to select a small mass element or in the rod with mass dm and length dx. The next thing that I need to consider is the mass per unit length of the rod. So the mass per unit length of the rod is simply the mass of the rod divided by the length of the rod. And this is something that's called a linear mass density. And so the linear mass density is a constant for the rod, since this is a uniform rod. So that means that if I divide the mass of the small element dm by the length of the element dx, that is also the linear mass density of the rod. But now I have a way to relate or express the mass of the mass element dm with the linear mass density of the rod and the length of the mass element dx. So the m is equal to the mass divided by the length of the rod times dx. So that is what I'm going to use to switch the variables of integration. So the integral that will calculate the moment of inertia becomes an integral of x squared dm. I'm replacing r squared with x squared since this is just a one-dimensional problem. And now I'm going to replace dm with the result that I got up here. And so the integral becomes an integral of m divided by L times x squared dx. I also must introduce limits for the integral now, since the rod has a finite size. And so the limits would be from minus L over 2 to L over 2. So the integral becomes m divided by L, that's a constant, it comes in front of the integration, times the integral from minus L over 2 to L over 2 of x squared dx. So this is a straightforward integral to do. So we get m divided by L times x to the third power divided by 3 from minus L over 2 to L over 2. When I write, the expression with the limits, I get m divided by L of L over 2 to the third power divided by 3 minus m over L of minus L over 2 to the third power divided by 3. So let's do the simplification here and see what we get as a final expression. So we get m divided by L to the third power divided by 24 plus m divided by L times L to the third power divided by 24, or that is 2 times m divided by L times L to the third power divided by 24. Finally, this is ml squared over 12. And so since the axis of rotation passes through the center of mass of the rod, that calculated moment of inertia is the moment of inertia about the center of mass for this rod. Now I can ask a different question, and that is, what's the rotational inertia of the rod about an axis that passes through the left end, parallel to the axis that passes through the center of mass? So the new axis of rotation is an axis that is parallel to the axis that passes through the center of mass. The question is, what's the moment of inertia about this axis right here? So in order to solve the problem, I must use the parallel axis theorem. The parallel axis theorem states that the moment of inertia about an axis that is parallel to the axis that passes through the center of mass is equal to the moment of inertia through the center of mass plus the mass of the object times the distance between the two axes squared. So the distance between the axis that passes through the center of mass and the new axis of rotation is equal to half the length of the rod. So h is equal to L over 2. So substituting the result that we obtained for the moment of inertia of the center of mass, ml squared divided by 12, and for h, substituting L over 2 gives us m times L over 2 to the second power. When you do the calculation, you end up with the moment of inertia about this new axis should be ml squared divided by 4.